involved in the analysis of Jet has also involved in the analysis of slope for open pit mine in North America and internationally. He is an expert of the shear strength and compressibility of steep fissure clays and has published of a number of geotechnical engineering topics. Yet is also a skill in numerical modeling using finite difference and finite elements technique. The presentation today is about stabilization of large landslides impacting Highway 73 in the Missouri River Badlands. So along a portion of Highway 73 west of the Lake Sakakiwa in the Missouri River Badlands of North Dakota. Landslide activity has been observed for several years. So today is a really good presentation from Jed. So Jed, welcome, and the public is yours.
Okay. Thanks, Julian. Appreciate it. Glad to be here, everyone. I did give a presentation about a year ago. That was about a project in the Dead Sea in Jordan. If you were there for that presentation, nice seeing you again. Glad to be with you. I'll be talking about the Highway 73 landslide stabilization. As Julian mentioned, what you're seeing on the screen is an artist's rendering of the final product. So that's where we ended up. And the presentation today will tell the story about how we got there. So here's a site map. Let's start in the lower left corner. This is the state of North Dakota. Here we have Montana, Minnesota, and then Saskatchewan here, Manitoba here. So it's fairly close to the Canadian border. This is the Missouri River that you can see on these county boundaries. You can also see the Missouri River here. It's dammed just downstream, so this is a reservoir, Lake Sakakawea. These are the Missouri River Badlands. There's a Highway 73, which we'll be talking about today. Of course, our site is on this red box. The Missouri River Badlands are known for having these high plasticity clays and shales. There's a lot of slope instability, especially as say a highway in this case is extending from the high ground to the west here to the lower elevations. There's a lot of headscarps, and we'll be talking about that more in the presentation. So that's the site. One thing to note, this is the Fort Berthold Reservation. So we're working on a reservation, which makes things a little more challenging with working outside the right-of-way, getting landowner permissions and so on, and that comes into play later on. Okay, this is the 2010 aerial imagery. So you're seeing Highway 73 here. This is the kind of the top of the bluff, the Badland area. And then we have what's called Bear Den Creek down here at the bottom, which is a tributary to the Missouri River. So going from northwest to southeast, we're high, and then we start coming down this slope and eventually cross this river, and then it goes back up on the other side. So it's crossing a tributary in this area. So that's the air photo from 2010. So now we get to May of 2011. You can see that on the upper portion road, here's that. This is looking northwest, so this is the high ground. You can see that we have some tension cracks, a little bit of vertical offset. Then we go about a week later. Looks like there's been more deformation. So here we're looking the opposite direction. You can see that Bear Den Creek area is down in here. There's the Badlands on the other side. So they're doing some drilling. This is before we were involved in the project. So this is another consultant doing the drilling. And then we go another week later, and you can see there's been more deformation. Here's the highway. You can see the pavement section fully exposed in this area. Obviously, the road is shut down at that point. So that's the spring of 2011. And they decided to do what they call a phase one emergency bypass. So they rerouted the highway. They were able to get it open, at least temporarily. That project was completed in September of 2011. Then there was a phase two roadway realignment and slide stabilization. So this happened the following year, where they wanted to do something a little more permanent. It turned out later that it was not permanent at all. Um, but this is the plan view. The original center line, the highway went through here. They rerouted the highway slightly upslope, and then uh, installed a drainage blanket at the bottom with some pipes. And I'll show in cross section now what that looks like. So here's the original highway. You can see the existing center line. Um, this material was removed, cut all the way down to here. Drainage blanket was installed with this pipe network. Fill was placed back in, and then the highway was realigned further upslope. And here's what it looked like during construction. So they've cut these benches down. I think this is just prior to when they would have started putting that drainage blanket in with the pipe network. Okay, so that project was completed in the fall of 2012. Now we're into spring 2013, and we have some tension cracks showing up on our new um, repair. And again, we weren't involved at this point. These are some historical photos. There's some problems starting right away. And then in the summer of 2013, we have another air photo. You can see there's some patches that have been placed, asphalt patches on the areas where the tension cracks were observed. Um, then we go to July of 2014. There was an emergency declaration, and it was obvious that something bigger was happening at this site. Likely that the failure was larger, deeper, and that realignment with the drainage system was too shallow to really solve the problem. So they wanted to allow time for a larger geotechnical investigation. And that's when we got involved a little bit later. But FHWA, that's the Federal Highway Administration. They met, they discussed options. They decided to split the project into two phases. Phase one, not to be confused with the previous phase one that I mentioned, was to perform some maintenance, some drainage improvements. There was some water that was ponding upslope of the highway embankment. They wanted to make sure that water was not infiltrating into the landslide. Um, about $500,000 for that work. And then a phase two permanent realignment or permanent repair. There was an estimated cost of $15 million for that work. So the two-phase approach was started in March of 2015. And again, that's about when we got involved in the project. So a quick summary of the site history. In 2011, there was a large slide, road closure. It was thought to be a rotational, shallow, and localized landslide. There was instrumentation that was installed. It measured the shear zone less than 50 feet below ground surface. I will say this is in imperial units, this whole job, so you'll hear a lot of feet and um, other units similar to that. Then October 2012, there was the road realignment that I mentioned, that subsurface drainage work. 2013, there's more problems continuing. So the DOT, North Dakota Department of Transportation, installed deeper instrumentation and noted that there was a deeper failure surface. So this was a larger landslide than initially determined. March 2015, there's this two-phase approach. They wanted to get this landslide fixed so they didn't have to go out and repair these failures, close the road, and so on. They wanted to have something more permanent. So fall of 2015, there were those some drainage improvements, and that's when we got involved in the project. So the constraints for the repair were uh, we couldn't shut down the road because if you shut down the road, the alternative routing is very far around. So they wanted to make sure that the traffic, at least one lane, was open at all times. Um, the construction had to be performed within the existing right of way, and that kind of gets back to the reservation land that I was referring to earlier. Um, the construction had to be in the right of way. The geotechnical investigation had to be within the right of way. And there couldn't be any permanent construction features outside the right of way. So now we go to spring 2017. I'll back up chronologically in the next slides, but just so you can see generally what the highway looked like when we were doing a lot of the geologic reconnaissance, geotechnical investigation work. It's in that same spot where they appeared in previous years. This is the headscarp of the main landslide. And as you look in the distance, you can see all these trees. Those trees are growing on the steep slope of sort of an ancient headscarp. And so it's right in line with that. And you can see it on this map of landslides from the Geological Survey in North Dakota. So our area of interest is right here. The pink areas are mapped landslides. I'll blow that up a little bit. The red is our Highway 73. We have a fairly large landslide here, and you can see where I showed most of the pictures of those tension cracks and the scarp crossing the highway was right here. So we went to the site and did some geologic reconnaissance. We wanted to understand truly the extents of the landslide. It was fairly easy to see that there was an ancient headscarp up here that had been reactivated. So here's the area where I show the tension cracks. You can see if you look closely, there's a patch of asphalt that has been placed. This is a later one than the ones we looked at earlier. So the green line is basic. That comes from GIS and looking at the topo data. That's kind of the steepest part of the hillside, and we looked at that as being the headscarp. Then it was important to find the extents of the landslide at the toe. And so this red line, we took a GPS unit out there. I did the mapping myself. We tried to find out where the toe bulge was. You can see where it crosses the highway here. And then we were close to, here's Bear Den Creek. So it gets very close to that in this area. And we walked all the way along this area and identified the extents at the toe. So how wide is the landslide? 1,500 feet wide, 3,100 feet long. So that's almost half a mile, a little over half a mile long. The road length impacted, 1,500 feet. And then the area was 85 acres. Landslide volume was 10 million cubic yards. This is a very large landslide, and the highway is crossing pretty much from top to bottom. Okay, so geotechnical investigation and instrumentation. There were 8 geotechnical borings. There were traditional inclinometers installed. There were shape arrays installed, and I'll talk about those in more detail later. And of course, vibrating wire piezometers to gather information on the pore water pressures. There was laboratory testing to develop primarily strength parameters, but also compressibility and seepage. The strength testing that was done, I'm not going to get into detail on that, but there's a lot of torsional ring shear testing done to understand the fully softened shear strength and also the residual shear strength of the high plasticity clays and shales out there. I mentioned the field reconnaissance, the scarp mapping. We wanted to understand the extents of the landslide. And then there were subsequent topographic surveys that were done to see if from LiDAR data, we could determine the extent of the landslide as well. And that was met with limited success. I'd say somewhat inconclusive, but it was helpful in some areas. Okay, here is a plan view of the geotechnical investigation locations. I will point your attention to these gray arrows. Those are areas, those are areas where inclinometers were installed, and this is the direction of the sliding mass. You can see there's a few down here at the toe, so almost straight east down here, and a slight northward component in this part. So shape arrays. If you haven't seen those, this is what it looks like. It comes on a spool like this. Some people call it like an electric garden hose. There are MEMS sensors in the shape array, and as you put that down the hole, you're able to determine deformation in terms of depth and magnitude. And I'll show some plots from that later. And our final installation looked like this. So it's out there. It's still reading data. We just got a download from it last week. So that's what the shape array looks like. Here's some data from an inclinometer. So if you haven't seen an inclinometer plot before, we have our depth over here. We have our cumulative deformation on the x-axis. And these are subsequent, these are all dates of these surveys. So there's an A axis and a B axis. The A is the axis that is generally aligned with the direction of slope movement. So landslide movement is going in this direction. Here's our shear zone where you can see most of the deformation occurring. Couple things. So there was an area in the southeast part of the landslide that actually had two shear zones. And so this plot, the black is showing the movement along the failure surface. This is in inches. And this is the deeper shear zone at this lower elevation. So you can see generally what that looks like over time. This is over a period of about 6 months, call it. And then the green is the upper shear zone. And you can see that one is fairly stable, although there's a little jump here when there was 1.4 inches of rain that fell. And then on the secondary y-axis over here, this is total head from a nearby vibrating wire piezometer. You can see a couple things to note here. When the total heads are higher, you can generally see that the rates on the black line are faster. So you can see it's faster rate here, slows down in here as the pore pressures come down. Then the pore pressures start going back up, and you can see the rate pick up. And then once it gets kind of to this higher level, it takes off even more. So no surprise there that there's a correlation between landslide deformation rate and pore pressure, but it's nice to confirm that this data. Here's another plot, very similar to the one that we just looked at, but it has cumulative precipitation now. So you can see that there's a larger storm event here. There's another one here. It corresponds to a faster rate here. Not a perfect correlation, but there is a correlation between the two. So what did we learn from the geotechnical investigation? Number one, it was a deep-seated translational landslide, not rotational. And I'll show a cross-section of that in a minute, moving between these elevations pretty consistently. High plasticity clay in the shear zone, which leads to low drained shear strengths, and there was a very low residual shear strength on the order of 5 degrees. I mentioned there was an additional deeper failure surface present at the southeast end of the site. And as I mentioned before, the deformation rate is fairly closely linked to the piezometer levels near the head scope. So how did we analyze this? We did a seepage calibration with GeoStudio, SeepW. We wanted to match the observed pore water pressures from the piezometers. Once we had that calibration done, then we looked at slope stability and a deformation rate calibration in FLAC. And I'll talk about that more later. And the parameters were generally consistent with the lab testing results, especially as it relates to the residual drained friction angle for the material. But it also reflects the scale of the area analyzed. Okay, so in plan view, we have three cross sections. Cross section 11 was our primary modeling cross section, although we looked at two more, 15 and 19. 19 primarily because that's where we had the two shear zones, so we wanted to make sure we were covered in that area. But cross section 11, this is about where those tension cracks and the scarps cross the highway. So we accounted for that. As I mentioned, we did finite element SeepW to calibrate the permeability of the materials and the boundary conditions. Then from that, we went into FLAC and we did the back calculation of the shear strength for the bad actor, which I'll show later. This was a coupled simulation because we wanted to account for the measured deformation rate. And then when it came to looking at the stabilization scheme, our soil structure interaction, we were able to do in FLAC with the drilled shafts that I'll be talking about. So here's our overall cross section. It's best to look at this zoomed in area. So a couple things to note. We have road fill in yellow. There's a little ranch access road here that you're seeing, but this is our main highway fill. There is some fat clay, lean and fat clay slump material that we determined to be kind of filling in this scarp area as material sort of washed down from here. And then here's our shear zone in red all the way through. You can see it dips at about 3 degrees towards the east. We were able to determine that from the inclinometers, also where that toe bulge was, which is way down here at Bear Den Creek. And then the other thing to note is there's a lot of lignite layers in this geologic setting. The lignite is important because it's generally high permeability, and that's what carries the flow primarily. So that was brought into the seepage calibration as well. So that's what our cross section looks like. And I want to talk briefly about the automated model calibration procedure that we used here. There's a lot of research that's been done and published on model calibration, parameter estimation, primarily for groundwater and environmental applications. When it comes to the geotechnical side, there's less, especially if we're dealing with deformation. So if you're trying to calibrate the stiffness along with other things such as permeability, there's not as much literature on that. So how does it work? No huge surprise here, but let's say we are doing a seepage model calibration. We have our permeability parameters for each of the materials. Put those into the model, run it, and your output is some kind of pore pressure distribution. And obviously you have some measured vibrating wire piezometers, let's say, in this case, and you want to compare your computed total heads to your measured total heads. So you have those. Then there's various methods that can be used to determine what the next set of inputs should be. And I'll talk about that briefly here. So in our case, we did a random sampling of the error function using a Monte Carlo. So here's the range of permeability values and boundary conditions for this problem. Do a Monte Carlo simulation and see what gets us closest to our measured pore pressures. Then you can do a more involved Newton-Raphson type iteration, where it's a method that helps project the direction that the permeability should go. Should the permeability be higher or lower for the next set of iterations? And then you can do some refinement, which I'll show on the next slide. So here, this is our number of iterations down here on the x-axis. On the y-axis is the square root of the sum of the square of the errors. So it's basically whatever your error is, measured minus computed. Take the square of that to get rid of the sign, and then you take the square root. So it's essentially an absolute value of the error. Our first 160 iterations or so were Monte Carlo. It's basically a shotgun blast. How do you, where's a starting point for the more sophisticated Newton-Raphson approach? So do that and get some permeabilities that are relatively close. And then you start with the Newton-Raphson approach, and you can see that our error is slowly getting lower, better. And then there were some manual refinements. Using this automated approach, it's a good way to determine if are there piezometers that are going bad. I just can't calibrate to this piezometer, and you might look into that one in a little more detail and determine that the piezometer's bad or there was something wrong in the installation record, and you might remove that from the calibration. So we were able to squeeze a little bit more out of it with the manual approach here at the end. And there were 11 parameters that we used for the calibration. So mostly horizontal permeability, but also some anisotropy. And then the total head boundary condition on the left side of the model. So what we're looking at here on the right, this is a table of those 11 parameters. These are the calibrated values for all the permeabilities, the anisotropies, and then here's the total head boundary condition down here at the bottom. And this is just showing, kind of zoomed in on the process that was going on. So our average error in total head between measured and computed was 3.2 feet. Seems reasonable to me. Our minimum was 0.5 foot. Our maximum was 6.7 feet. Okay, I mentioned we needed to do a residual strength back calculation. So this is the FLAC model. I apologize that it's small and a little hard to see. But what you're looking at in green is the maximum shear strain rate. So that is our that's where our shear zone is located. So it's dipping down towards Bear Den Creek over here at about 3 degrees, as I mentioned. One thing to note is the drain friction angle for the fat clay in the shear zone. We broke it into two. There's kind of a back slope portion here, and then there's the rest of it. And so the primary calibration was done on this material here, 5.3 degrees for a residual friction angle. And as I mentioned earlier, that matched fairly well with the torsional ring shear testing that we did in the lab. Okay, so we did model the selected repair option, and I'll talk about that more later, but here's our effective vertical stress for existing conditions. Here's our pore water pressures in FLAC. Here's our factor of safety of 1 back analysis. So that's what got us our 5.3 degrees for a residual friction angle along here. And then eventually we installed some drilled shafts here. And it's a little hard to see, but in white, that's the bending moment diagram for the 2 rows of drilled shafts. And this was an early iteration here, so there was some refinement after that. Our target factor of safety was 1.25. And that's a published value from other departments of transportation for a landslide stabilization. Why can you get by with a lower factor of safety? Because there's greater certainty in the material parameters because you're doing a back analysis and you're starting from a factor of safety of 1.00 in this case. Okay, deformation modeling calibration. This is a plot of inclinometer displacement in inches versus time. And there's various locations where we were measuring, but in general, you could see that the displacement rate was about 1.79 inches per year. So we knew that this landslide had that velocity, and we wanted to account for the momentum in the FLAC model because the landslide's moving. Then we put the drilled shafts in, and what is our post-stabilization deformation rate going to be? And so the way we did that in FLAC is there's some parameters that you can adjust such that it will adjust the time scale in the model, and you can match this deformation rate. So once you have calibrated pore pressures and you have a factor of safety of 1.00, this is an actively moving landslide, and the rate is correct, then in FLAC, you're ready to install the drilled shafts and see what the resulting factor of safety is, and also the post-stabilization deformation rate. Okay, to repair the slope or not repair, there were three alternatives. You could do nothing. You could realign the highway, and that's a major realignment, not just the offset that was done previously back in 2012. This is a more significant realignment, or maintain the current alignment and do repairs within the current alignment of the highway. Those are the three alternatives that were examined. Alternative one, if you do nothing, you probably have to reduce the speed limit on that section of highway. There would be ongoing maintenance. There'd probably be some temporary shutdowns for the maintenance, or if there's a large slump that occurs, say in the spring, you might have to shut down, or there could be a permanent shutdown even. But that did not meet the purpose of the project, so do nothing was out. I'll skip over that one. Looking at a realignment, you can see how far around you'd have to travel if this section of a highway were closed for whatever reason. Okay, so this is the alternative two with the realignment that's relatively close to the project, but not crossing the scarp here. So this is the existing Highway 73 alignment, and what was discussed was something that is offset to the west. It stays above that headscarp that you can see with the green vegetation here. But then the issue was it was going to have to extend to the southeast and come down the bluff at some point anyway, and then come back up. There was some instability in this area as well. Plus, there was this blue gas pipeline that was in the way. I got really close to that. It was determined that while you avoid most of this landslide, you still have to deal with some slope instability here. There could be large fill areas. The idea was to keep the alignment where it is and repair it in place. So that's alternative three, maintain the current alignment. That's what was recommended. The concept was one interceptor trench within the right-of-way and 2 to 3 rows of drilled shafts within the right-of-way. And the cost, $13.5 to $18.5 million at that level. So here's how it came out. This is the drilled shaft alignment in blue. And then we have the interceptor trench alignment here. So very close to the edge of the right-of-way. But as I mentioned earlier, all of the repair work had to be done within the right-of-way. So that limited our options to some degree. So similar to what we were looking at before, the interceptor trench would go here. And the idea would be to capture any water that's coming in from these lignite seams. And then the drilled shafts, this shows 3 rows. Most of the alignment had 2 rows, but in the area where we have the 2 shear zones, we went to 3 rows of drilled shafts there. So here's what the trencher looks like to install the interceptor trench. I have a video that I'll show in a minute of that. The drill shaft design concept. We have a distributed load on the piles from the moving landslide. That applies a moment to them. There's an axial force, although the axial force is quite small. And the layout looks something like this, where you have some arching going on in between the piles in plan view. And then you can see when we have 2 rows, we would stagger them like this. In FLAC, you're able to do a plan view model. It's a push test. So you're able to take a pile like this or a drilled shaft, and you're able to push it into the soil. And it comes to some limiting response, and you're able to take those limiting shear strength values and then put them in the 2D cross-section model. And it accounts for the soil structure interaction that way. Here's what the drilled shafts look like. There's a reinforcing cage. I won't get into a lot of detail on this, but they were 5 feet in diameter, 2% steel by area. And then we wanted to make sure that we did some sensitivity on how deep the drilled shaft should be below the shear zone. And we determined that 20 feet was the magic number. So wherever the shear zone was, we were going 20 feet below that, all the way along the alignment. Here's what the alignment looks like. So these are slide, and then on the far side, you can see the interceptor trench. It's a little hard to see. Trencher looks like. This is the pipe that's going in the bottom of the interceptor trench. So it's a filter aggregate with a pipe in the bottom. This is actually a video. I think I'm going to skip the video, but generally, it's like a giant chainsaw, essentially. It's digging the trench. They're placing the granular material in this hopper, and then as it excavates the material out, it comes off this conveyor right here, and then you can see the pipe going in the bottom of the trench over the top. Oh, I guess it is playing. I don't know if we'll watch the whole thing. You can see them putting the granular material in, and then you can watch this conveyor belt here. It'll start bringing material out. You can see kind of that clay material that's being excavated out of the trench. Then you get some kind of slop over in this area. So that's what construction looks like there. Here's another video closer up. You can see some water in this area. There's that conveyor belt coming off, and there's that hopper again. So here's the outlet of that interceptor trench. You can see during installation, the water's a little muddy. But then later on, that's what the flow looked like coming out of the interceptor trench. When I was on site, it was crystal clear. So decent flow rate coming out post installation. Okay, the drill shafts. I'm just going to show a few pictures of the installation. Here they're tying the reinforcing cages. You can see that. They're lifting up the cage. Here they're setting it. It's going down the hole. Placing the concrete. They're placing the concrete via free fall here. And that's what a completed drilled shaft looked like. And then, of course, in the end, they covered it up with topsoil and you don't even know it's there. So here's that rendering again, just as a reminder. So how did things look in the end? What does our monitoring data show? So this is total head being plotted from 4 different piezometers that were installed. I think the blue one is the most instructive because that was installed way back in 2014. This is a vibrating wire piezometer connected to a data logger. Um, so you can see generally the pore pressures were in the range of 2050, maybe a little bit higher than that. The interceptor trench was installed here. You can see there was a significant drop in the heads. And then, I mean, this is 2018. And then we just downloaded the data last week. At some point, that piezometer failed, but it got data through last fall. And you can see that it generally stayed low throughout. There were a few points where it came up a little bit. And you can see that other piezometers in the area came up even more. But generally speaking, the pore pressures have remained low. So about a 15-foot drop in total head in general throughout the landslide. So the interceptor trench worked, and what we're looking for is it possibly getting plugged at some point? But we designed the filter aggregate such that it was a natural filter. And so far, it's working great. And then this is kind of the money plot here, post-stabilization monitoring. So what did we predict with FLAC for the deformation rate? So what we're looking at here is this is our 1 year of deformation that occurred as part of that deformation calibration. So I mentioned it was 1.79 inches per year. And so here we are after 1 year at 1.79 inches. Then the red line is what do we predict for the deformation of the slope after stabilization? And you can see that after 4 years post-stabilization, we predicted 0.1 inches. It's this little gap right here. So you get 2 inches, 1.5. So about 0.1 inches in 4 years. What does the data show? This is from a shape array. This yellow line is 4 years after stabilization, 0.1 inches. Maybe it was dumb luck. Maybe we were onto something with the deformation rate calibration, but it worked out really well. There was some data downloaded after this that showed basically the same trend. It's holding with this. I didn't have time to process it, but the deformation rate is doing exactly what we thought. We told the client from the beginning that we're not going to stop the landslide cold, but we are going to reduce the rate of deformation to a level that's so small that it's manageable. Project aftermath. The project did win an award, 2020 Engineering Excellence Award. This is from the American Council of Engineering Companies in North Dakota. What am I showing here? This is Google Street View. You're seeing where that interceptor trench comes out right there. So there's no evidence that an interceptor trench has been installed. All the vegetation has been reestablished. And then you come to the other side. Now we're looking back down slope. So the drilled shafts are all the way along here, and you have no idea that they're installed. So if you were to drive this road for the first time, you would have no idea that a major construction project happened in that area. But we've been pleased with the results post-stabilization. That's all I have. Any questions?
Okay, thank you. Thank you, Jeff. Really interesting presentation. So anyone has questions? Please unmute or can write in the chat. Any questions at all, guys?
If none, that's fine. You could reach out to me later if any questions come up.
We have in the chat, probably how deep the intercept trench was from the natural ground.
Installing an interceptor trench, there's a cost trade-off there because if you want to go to certain depths, they need to bring in a much larger piece of equipment. So there's a big jump in cost. So 30 feet was kind of the optimized depth to be able to keep costs down, but also draw the pore pressures down to where we needed them to be.
Okay, I have a question, Jeff,
Mhm.
about the calibration, about the FLAC model. How many models do you perform in order to get the displacement or to get that is a good approximation of the real problem or the real measure in field?
The deformation rate or the pore pressures?
The deformation rate.
Yeah, the deformation rate, once we had the correct permeabilities and pore pressures in the model, and we had done the calibration, the back analysis to get a factor of safety of 1.00. Once the model is to that point, um, then you're changing the one parameter that controls the time step, the bulk modulus of water. You're just changing that manually and looking at what's the deformation rate that comes out after running the model transient, fully coupled for a year. Um, and and then yeah, if you need to adjust that parameter manually, you can. I don't remember how many iterations it took, but it wasn't that many, maybe five, something like that. What
Was
takes
okay.
a lot of iterations is the seepage calibration using that Newton-Raphson method. But that wasn't done in FLAC. That was done in GeoStudio. The runtimes are a lot faster, and um, GeoStudio was a better tool for the seepage calibration.
Okay, thank you. Other
Mhm.
question here. Any advice when characterizing a landslide? Where and how many inclinometers, piezometers should be installed?
Yeah, to answer the second question, it really depends on the size of the landslide. Here we had a fairly large landslide. Um, And so you can see there were quite a few inclinometers that were installed, and some were installed before we got involved in the project as well, and piezometers. But it really depends on the scale. Um, if you have a reliable inclinometer and it's in a good spot and you think it'll last a long time, then yeah, maybe for a small landslide you can get by with one and it'll be just fine. Um, but for a large one like this, we had to do quite a bit more. I will say here we were limited by the right-of-way constraints. I would have loved to have an inclinometer down at the toe just to confirm that we had the right shear zone and we had the right dip for that layer. So we had to kind of rely on the geologic mapping in that area. But we did a back analysis, and when you do a back analysis and start from a factor of safety of 1.00, that kind of covers some sins. We could have been off on that dip a little bit, and it probably wouldn't have changed the stabilization results much in the end because we're starting from that back analysis. So it's kind of a roundabout way of saying it really depends on the site conditions, the scale of the problem, on how much instrumentation needs to be installed.
Thank you, Jay. Other questions? There is other question, guys. Well, okay. Thank you, Jet. Thank you
Okay.
for sharing with us. Okay. See you then.
Okay. Thanks for everyone's attention.
Thank you, everyone.